Hello, good afternoon. Do you hear me?
Yes, sir. Yes, sir.
Okay, fine, perfect. So, shall I share my screen now?
Hello?
Yeah, please tell me. Noise ఏమైనా ఉందా అండి? బ్యాక్గ్రౌండ్ నాయిస్ కానీ ఏమైనా ఉందా? పర్లేదా?
లేదు సార్. లేదు సార్, క్లియర్ గా ఉంది.
ఓకే అండి, ఓకే.
నా వాయిస్ బాగానే ఉంది సీనియర్.
మీది బాగుందండి.
ఓకే సార్, ఓకే సార్. 2 minutes సార్, జస్ట్ 2 minutes, 5 minutes వరకు స్టార్ట్ చేస్తాం సార్.
ఓకే, నో ప్రాబ్లం. ఓకే అండి.
2 o'clock అవగానే స్టార్ట్ చేసేద్దాం సార్.
ఓకేనండి. ఇప్పుడు పార్టిసిపెంట్స్
సార్,
పార్టిసిపెంట్స్ ఎవరు ఇప్పుడు ఈ ప్రోగ్రామ్ లో?
పార్టిసిపెంట్స్ సార్
అంటే స్టూడెంట్సా లేదంటే ఫ్యాకల్టీనా అండి? వేరే డిఫరెంట్ కాలేజెస్
అందరూ ఉన్నారు సార్. ఫ్యాకల్టీ ఎక్కువ మంది ఉంటారు సార్. ఇది అసలు వినపట్లా.
హలో, నేను పెంచుతాను, ఒక్క నిమిషం వాయిస్ పెంచుతాను. పార్టిసిపెంట్స్ అంటే స్టూడెంట్సా లేదంటే వేరే ఫ్యాకల్టీ, వేరే కాలేజ్ ఫ్యాకల్టీనా అండి?
సార్ అందరూ ఉన్నారు సార్. అందులో మనకొచ్చిన దాంట్లో ప్రొఫెసర్స్ ఉన్నారు, వేరే ఫ్యాకల్టీస్ ఉన్నారు, అసిస్టెంట్ ప్రొఫెసర్స్ సుమారు ఒక 400, 500 మంది ఉన్నారు. రిజిస్టర్ చేయించుకున్న వాళ్ళండి.
ఓకే ఓకే.
మళ్ళీ అందులోనే మళ్ళీ స్టూడెంట్స్ కూడా ఉన్నారండి. ఒక 10% ఎంతో స్టూడెంట్స్ ఉన్నారు.
అంటే మొత్తం ఎంత ఆల్ ఇన్ ఆల్ ఎంతమంది ఉన్నారు మొత్తం?
మన దగ్గర రిజిస్టర్ చేయించుకున్న వాళ్ళు 1587 మంది చేయించుకున్నారు సార్.
అంతమందా? ఆహా! ఓకే
సపోజ్
ఓకే.
అందరూ అటెండ్ అవుతారని లేదండి, కొంతమంది అటెండ్ అవ్వట్లేదు.
ఓకే ఓకే.
సో 75% లెస్ దాన్ 60% అలా అటెండ్ అవుతున్నారు.
60% అయినా కూడా హ్యూజ్ నెంబరేనండి.
అంతే సార్.
వెరీ బిగ్ నెంబర్.
మనం 67 మినిమం 700, 800 ఉంటారు సార్.
ఓకే
600
ఓకే.
సార్.
ఓకే.
అంటే సేమ్ డే వేరే కూడా ఉంటాయి కదండి. కొంతమంది
ఓకే
ఇటు
ఓకే.
వచ్చి ఇలాగా దేర్ ఆర్ డిఫరెంట్ టైప్స్.
ఓకే ఓకే.
మీకు కంఫర్టబుల్ గానే ఉంది సార్ అక్కడ?
నో ప్రాబ్లం. ఇబ్బంది ఏం లేదండి.
సార్.
నాకంటే మేడ మీద షెడ్ ఉందన్నమాట. పిల్లలు రారు, డిస్టర్బెన్స్ ఉంటే తలుపేసేసుకుంటాను అనమాట. కింద కూర్చుంటే వాళ్ళు డిస్టర్బ్ చేస్తారు, తలుపు కొడతారు, లేట్ నెట్ ఆఫ్ చేసేస్తారు, అన్ని చేస్తారనమాట. సో అందువల్ల ఏంటంటే లాక్ చేసుకొచ్చేస్తాను. మేడ మీద వచ్చేవాడు మెట్ల దగ్గర లాక్ చేసేస్తాను, ఇంక పైకి రారనమాట.
సార్.
సో హౌ ఆర్ థింగ్స్ ఇన్ యువర్ ప్లేస్ సార్? ఎవ్రీథింగ్ ఈజ్ ఫైన్?
ఫైన్ సార్. అయితే మాది కూడా కొంచెం బాగా ఇదిగా ఉంది. కోవిడ్ ఇబ్బందిగానే ఉంది మాకు.
ఓకే.
వాళ్ళు గవర్నమెంట్ వాళ్ళు కాలేజెస్ వాటిలో కూడా తీసుకుందాం అంటున్నారు. హౌ దే విల్ డూ ఇట్ ఇంకా తెలియదు ఇంకా.
ఓకే. కానీ చాలా వస్తున్నాయండి అక్కడ ఆంధ్రాలో, కేసులు విపరీతంగా వస్తున్నాయి.
సార్ కేసెస్ చాలా ఎక్కువ వస్తున్నాయండి. ఆంధ్ర తెలంగాణ రెండు కూడా 1 by 1.
కానీ ఎడిపోతుందో తెలియట్లేదండి పరిస్థితి. ఎప్పటికీ మామూలు రోజులు వస్తాయా అనిపిస్తుంది.
సరే లైవ్ స్టార్ట్ అయిందండి మనం.
ఓకేనండి. యా. సో షల్ ఐ వెయిట్ టిల్ 2 o'clock or you want me to start now?
ఒక 5 minutes అవుతాను సార్. 2 o'clock.
No problem. Okay, fine. Okay. నేను స్క్రీన్ షేర్ చేశానండి. వచ్చిందా మీకు అది? సో డిడ్ యూ గెట్ ద స్క్రీన్ దట్ ఐ షేర్డ్? హలో.
ఎస్ సార్. వచ్చింది సార్.
ఓకే then fine, perfect. So shall I start now? It is 2 o'clock. Hello.
Sir.
Shall I start now?
Sir, I'll give you a small introduction, sir, please.
Okay, sir. Okay, sir. Whenever you want, okay, I'll start. No issues, sir.
Sir. Okay. Good afternoon to all. This is Dr. R. Subbarao, convener, Faculty Development Program on Mathematical Prototypes and its application Engineering and Science. We are entering into the third day of this FDP. Today, I am very highly privileged to and truly honored to introduce Dr. Challa S. Sastry, who is one of the most prominent academic personalities and eminent scholar. He is known as a man of metal because though his education and brought up is in a small town, Machilipatnam, he could drive himself to the heights in a indefatigable spirit. He did his bachelor's degree BSc in Hindu College, Machilipatnam, MSc Tech in JNTUH, Hyderabad, PhD from IIT Kanpur with a dissertation on wavelet-based multi-resolution methods in computerized topology under the guidance of Professor P.C. Das. Currently, he is a professor of mathematics in IIT Hyderabad. Before this, he had a professional experience at the University of Hyderabad initially, later at the University of British Columbia, Canada, and at Indian Institute of Information Technology, Design and Manufacturing, IIT-DM Jabalpur. His research interests are wavelets, sparse representation, theory, and inverse problems. 3 PhDs has been awarded under his esteemed guidance, and 5 more members are pursuing, 3 for doctoral degree and 2 more for postdoctoral degrees. As far as his publications are concerned, he has an extensive range of 64 publications in various national and international reputed journals, and which made a remarkable sum of 426 citations. Sir, we are in fact extremely fortunate to have you here amidst us and to hear your talk on mathematics behind machine learning and also on numerical linear algebra theory and applications in medical images. Thank you so much, sir. With this brief introduction, I invite Dr. C.S. Sastry Garu to take over the session and discuss on the topic. Thank you.
Yeah. So good morning, everybody. Sorry, good afternoon, everybody. So firstly, I am thankful to Professor Subbarao Garu for the opportunity. So I'm going to talk about, of course, there are 2 parts in my presentation. So the broader picture is numerical linear algebra and its application towards machine learning. This is what I'm going to talk about. Okay, so let us take a look at what numerical linear algebra stands for. I think I did not share, right? Yeah. So let us take a look at what numerical linear algebra stands for, along with its potential for real life applications. So there are, of course, these are some of the fundamental problems that one may come across in the real life domain. So we all know in many applied domains, we end up dealing with a matrix equation y is equal to ax. So our task at that point will be to solve this equation. Okay, you know, of course, there are several methods available in the literature. Okay, so there are many elementary methods like inversion method, Gauss-Jordan method, Gauss elimination method. So many methods are available in the literature, even Cramer's rule. But unfortunately, most of those methods actually collapse in real life domain. Reason is that in real life domain, one has to deal with a matrix equation where the size of the matrix actually runs into millions and lakhs and millions. Okay, I'm going to talk about one application. There you will see that the size of the matrix will be of the order 10 lakhs by 10 lakhs. If that is indeed the case, no method actually works. Then we have to have some smarter ideas to be able to get the solution of that matrix equation. So this is one fundamental problem, which is actually solving matrix equation that one comes across in real life domain. Okay, on the other hand, See what normally happens. One actually poses the problem of getting a solution to matrix equation in some optimization setting. So we are going to see that optimization techniques actually play a pivotal role in several real life domains, including machine learning. The other fundamental problem that one comes across in real life domain is least square problem. Okay, let us see actually what it means. Suppose that we have the same matrix equation where y is equal to ax, where a can be fat and short matrix. I mean to say row size is small compared to column size, or a can be tall and slim matrix. I mean to say that the matrix actually a can have a bigger column size compared to row size. If second one is indeed the case, then what happened? The system in general doesn't have solution. So I am dealing with the case where in the matrix equation y is equal to ax, column size is very, very big compared to row size, which means A is a tall and slim matrix. Okay, if this is the case, in general, this matrix equation doesn't admit any solution. Like for example, imagine in the xy plane you have three equations. So there in general, there cannot be a point common to all three equations. Then what is it that we have to do? We have to settle for a point that lies closest to three lines, as closest to three lines as possible simultaneously. So that is indeed the approximate point, or which is considered as an approximate solution of the matrix equation, because there is no x satisfying y is equal to ax, right? So in such a case, what one does, one actually finds x in such a way that the distance between ax and y is minimized. Okay, so such an x actually can be solved by solving this matrix equation. This is simple optimization problem. This will boil down to this kind of matrix equation: A transpose A whole inverse A transpose x is equal to A transpose y. So this is again in the form of some new equation bx is equal to say some new y, y1. So which is exactly same as solving the matrix equation. Okay, so even in this case, one has to deal with the matrix equation. The other prominent problem in numerical linear algebra is eigenvalue problem. Okay, we all know there are methods, of course. When A is a square matrix, okay, we all know basically the eigenvalue is essentially the lambda, which satisfies determinant of A minus I into lambda into I is equal to 0, right? So that is essentially eigenvalue problem. Imagine, so determinant of A minus lambda I is equal to 0 is essentially polynomial in lambda of degree n. Suppose A is very big number. Okay, then again, that is essentially what? Finding the root of some polynomial of degree n. Okay, so let us look at one real life application of eigenvalue problem. This is essentially Google search. We all know Google search is based on eigenvalue problem. So there was a paper written by one of the founders of the Google. The title of the paper is like this: $25 billion eigenvector, the linear algebra behind Google search. This paper, of course, appeared in Siam Journal, Siam Review, way back in 2006. So this tells you the potential of the eigenvalue problem. So I talked about three problems here, which are essentially fundamental problems in numerical linear algebra. One is about solving the matrix equation. Okay, A can be anything. A can be square matrix. A can be fat and short matrix, tall and fat and short matrix. I mean to say row size being smaller than column size. A can be tall and slim matrix. I mean to say that the column size being bigger than row size. This is one fundamental problem. Many real life applications at some point actually will boil down to solving matrix equation. The other problem could be that finding x when the system doesn't have solution, then we have to of course settle for approximate solution. The problem of finding the approximate solution is posed as an optimization problem, which is about minimizing the distance between ax and y, which in turn actually leads to this matrix equation A transpose A whole inverse A transpose x is equal to A transpose y. This is again in the form of matrix equation. The other fundamental problem is eigenvalue problem, right? And the matrix A has very huge size. So finding eigenvalue and of course finding the eigenvector could be basically intractable. What I mean to say, the complexity actually will be too huge. So one has to have smarter ways. I'm not going to talk about eigenvalue problem in the latter part of my presentation. Let us look at the smarter way of finding matrix solution of matrix equation. Okay, so before I actually move further, I'm giving you the outline of my talk here. In the first part of my presentation, I'll stick to solving matrix equation, right? For so-called sparse solutions. And after talking about the theory, I'll demonstrate as to where such a solution plays out. While in the second part of my presentation, I'll talk about mathematics behind machine learning. So here again, we will see that the methods that we study in numerical linear algebra or linear algebra have prominent role to play in machine learning. Okay, so to begin with, let me actually concentrate on the first part of my presentation, which is just merely about solving matrix equation. So I start with application to begin with. Okay, the application is in computerized tomography or CT scanning, or sometimes it is referred to as CAT scanning. So in computerized tomography, what happens? A patient is made to lie on the bed. The bed actually goes inside the machine. Okay, suppose the forehead part, suppose the person actually has some tumor inside his head. The object is to determine the structure of the tumor. Then some radiation X-ray dosage is given to the patient. So based on that, some image actually will be displayed, and doctors actually will get to see that, and they'll make their interpretation about the structure of the tumor. But in this process, actually, there is a lot of mathematics. Let us try to understand what that mathematics is. See, imagine a typical structure. Imagine this is the cross section. The blue portion refers to the cross section of the head. Okay, for that matter, it can be any part of the body. Okay, this is the head. Now, several X-rays actually are made to pass through the cross section. Once they pass through the cross section, they lose energy. Okay, take for example a typical ray. So once this ray, typical ray, emerges out of the cross section, it loses some energy, and that energy loss is measured. So this energy loss is measured by the CT machine for every ray. So we have several set of parallel rays. Then the source actually moves for a different angle. So for different angles, essentially, energy losses are measured. So now system gives you energy loss corresponding to every ray. So what is it that we have to do? Based on the energy loss, we have to determine if you take a particular location in the cross section, which is referred to as a pixel or cell. Okay, so objective is to determine how much energy that particular cell absorbs. Okay, so that can be done in using mathematical technique. This is what I'm going to talk about. This is one way of actually measuring energy losses. The other way of measuring energy losses is through what is called fan beam geometry. So point source actually, from the point source, several rays actually emerge out. They hit the cross section, they come out of the cross section, energy losses are measured. This is essentially for faster data acquisition. Why this is required? During a scanning process, a patient may move because of, or they can be deep breathe, or they can be cough. Because of this, there could be error in the measurements. So for all these practical reasons, so one has to acquire data in almost no time. So faster data acquisition really has important role to play in medical domain. So this is, so mathematically, what is to be done? Energy loss, this P refers to energy loss for every ray, and F refers to the image. XY refers to a particular location in the image. So let us now this is of course a kind of story. Let us understand this problem in mathematical terms. I am taking a particular ray, X-ray. Okay, imagine the cross section is basically covered through some grid. Imagine your cross section is somewhere inside this grid. Okay, now this is a typical ray, which is actually emerging through the cross section like this. So you give some numbers to the cells. Imagine your cross section is divided in the form of a square grid, square or rectangular grid. Okay, give some numbers to each and every cell, 1, 2, 3, 4, so on up to n square. So essentially this grid is of size n by n. Okay, now this particular ray is actually hitting these cells or these locations or these pixels. We already know what these cells are. Suppose for a given ray, this is I1th cell, this is I2th cell, this is I3 cell, so on, this is some IL cell. So what system measures here is the energy loss. I know initial energy because I have control over the energy of the ray. I know basically the energy of the ray that is actually coming out of the cross section. Again, this is measured by the CT machine. So the energy loss is essentially what? I0 minus I1. I know essentially only I0 minus I1, nothing else. Of course, this is for every ray. So knowing this, what we try to do here is how much energy that each and every cell can absorb. See, for this particular ray, these are the cells actually falling in the path of the ray. If you take some other ray, for example, some other set of cells actually will fall in the path of the ray. Put it in mathematical terms. As I stated already, along the path of the ray, these are the cells I1, I2, so on, IL. which are actually falling. So energy loss now is essentially EJ, which is equal to I1J minus IJ1, which is nothing other than essentially the energy absorbed by I1th cell, the energy absorbed by I2th cell, the energy absorbed by IL cell. Okay, so the sum of the energies absorbed by the pixels that will fall in the path of the ray is essentially equal to energy loss. So this can be actually reposed in this form, a big row into a big column. Okay, the column has components P1, P2, so on Pn square, right? So where do we have ones here? I have one here corresponding to I1th location. I have one here corresponding to I2th location. So what are the pixels actually that are hit by the ray? In those locations, I consider 1, elsewhere I take 0. This is of course for a typical ray. Suppose actually there are several rays. Okay, now for each and every ray, I can actually have this kind of equation, rho multiplied by a column. So for several rays, essentially, suppose you take m number of rays. So I have basically energy loss corresponding to m rays, namely E1, E2, so on Em. Okay, matrix whose elements are only zeros and ones into P1, P2, Pn square, right? So this is exactly now in the form of matrix equation. What is known to me here? This left hand vector E1 to Em is completely known to me because the components in that vector refer to energy losses which are measured by the CT machine. Again, this matrix is also known to me because I can just use the idea of some simple trigonometry and identify where zeros and ones are present in this matrix. So in that sense, actually, this matrix is also known to me completely. This is known to me completely. So what is it that we have to find now? Only this vector P1, P2, so on Pn square. Okay, so the problem of recovering image in CT can be recast in the form of matrix equation, just y is equal to ax, right? Nothing big about it. Now, this is where actually we run into problems. Let us see actually what that problem is. Okay, in medical domain, typically one deals with an image of size 1024 by 1024, which is essentially megapixel image. Okay, but so n here is 1024, so n square is 1024 whole square, which is more than 10 lakhs. Okay, suppose you supply all, suppose the patient is given full dosage. Then what happens? This becomes a square matrix whose size is about 10 lakhs by 10 lakhs. And this vector is of size 10 lakhs. Okay, around 10.5 lakhs. This is matrix of size 10.5 lakhs by 10.5 lakhs. This vector is of size 10.5 lakhs. Okay, now can we actually, if we apply standard methods, it is very difficult for us to get a meaningful solution of this matrix equation. Right, so real life domain is now throwing actually one challenging problem. That challenging problem is what? About inverting the matrix whose size is running into lakhs. Okay, it is about 1 million. Row size is about 1 million, column size is about 1 million. So no actually known method actually, or no actually standard method works in this case. So we have to have a smarter way. Okay, let us actually end. So before this, but what happens in medical domain, patient actually should not be given too much of dosage because X-rays are harmful to the human bodies. So if you look at this carefully, this M is actually referring to number of X-rays. Okay, so in order to give lesser dosage to patient, what is it that we have to do mathematically? Mathematically, we have to reduce this number, right? So when we reduce this number, this system essentially becomes an underdetermined system, meaning that the row size is very, very small compared to column size, right? So keeping the real life requirement in mind, I want to cut down on this number, right? Now a question arises, how small this number m can be so that when I invert, the solution I get is actually faithful, because I cannot afford to have a bad image, right? So I want it, on one hand, I want to actually have a smaller value for m. On the other hand, I have to keep in mind that the vector P1, P2, Pn square that I get should be good enough, in the sense that the image that I get out of this vector should be good enough. So I have to strike a balance between taking smaller value for m and having good quality for the image that we get out of this matrix equation. Okay, so this is where I think we try to have a smart play. Let us actually understand that. This is a typical CT image. This outer rim, actually this white rim refers to this skull portion. Okay, doctors have some interpretation about this image. If you look at this carefully, this image, only about 42% of the values. For us, of course, mathematically, every image is a matrix, right? So in this matrix, or the matrix corresponding to this image, only about 42% of the pixels are non-zero, rest of them are zero. which means there is some property that is naturally present in this image. On the other hand, look at one more property carefully here. That property is what you have a kind of piecewise constant region. See here, I have ellipse here. In this ellipse portion, all pixel values are constant, or all elements actually corresponding to all elements in the matrix corresponding to this ellipse portion have same value. Similarly, the elements actually that fall in this portion have same value. The elements actually that fall in the outer rim portion have same value. Similarly, in this portion, the elements actually have some other value. So there is a kind of piecewise constant behavior that is also naturally present in the image. Okay, the question now is, my objective is clear to me. What is my objective? My objective is to give lesser dosage to patient, right? Because that is my ultimate requirement. Of course, I have to keep in mind that the image that I reconstruct should not be bad. It should be actually good enough, because we cannot afford to have a bad image. Okay, so now this is the property we want to exploit. Look at this. If you take the gradient of this image, when I say gradient, I mean to say that you just take consecutive difference between pixel values. Okay, this is matrix for us, something like A21 minus A11, A31 minus A21, A41 minus A31, like that. Actually, you take difference between consecutive pixels. Because of this piecewise constant pattern that is naturally present in this image, so that is essentially like taking the gradient of the image. In that gradient domain, only about 12% of the pixels are non-zero. Rest of them are zero. So what is this signifying? This is signifying that I have this mat now. So we have observed actually a couple of things here. Those are what? In this matrix, many components are zero. Obviously, look at this. Take a first row. In the first row, only very few ones are present. Similarly, the same property holds, okay, corresponding to each and every row, which means this matrix is highly sparse. So I know essentially where ones are present in this matrix. So this matrix is also giving me some property. Number one. Number two, here in this vector P1, P2, so on Pn square, I have noticed that if I take gradient of this vector, essentially I have only about 12% of these components Pi are non-zero, rest of them are zero, which means this vector in gradient domain is highly sparse. So when I say a vector is sparse, I mean to say that very few components are essentially non-zero. So I have these properties. Now we will see that this is completely mathematical treatment. See, application is coming from medical domain, but the treatment is coming from mathematical domain. So we have carefully observed the properties that are naturally present in the given CT image. Now keeping all that in mind, what we are trying to do, we want to actually make use of the properties of this matrix as well as this vector. This is of course unknown to me completely, but there is a property. We would actually exploit that property. What is that property? That property is in the form of sparsity of this vector P1 to Pn square. Property of this matrix is what? Very few components are, or very few elements in this matrix are non-zero, and many of them are zero. Okay, so making use of these two properties, we can show that in fact M can be made small. Instead of taking 1024 whole square number of X-ray samples, one can as well have 1/4 of, in fact, the total number of X-rays, so that at the same time one can ensure that the reconstruction can be of very good quality. Okay, so the mathematical treatment is giving us completely faithful solution. The mathematical treatment is giving us reliable solution. The mathematical treatment is telling us as to how to reduce the dosage to be given to the patient. Okay, now, of course, this is application. Okay, application is what now this, so this particular application is telling us to solve, sorry. So this particular application is telling us to solve this matrix equation for a solution wherein very few components are non-zero. What I mean to say is, to repeat, this particular application is telling us to solve this matrix equation for a sparse solution. The solution with very few non-zero components. So now this is what we are interested in. There are in fact many other applications where one would like to solve matrix equation for a sparse solution. Umpteen number of applications are available. Okay, I'm not going to touch those applications, but I just emphasized one application where one would see the importance of sparse solution. Now let us look at theory, mathematics behind it. Then okay, we can come back to application. So now let us understand the mathematical setting. The mathematical setting is what? Suppose I have a matrix equation. So my objective is to solve this matrix equation, nothing else. Okay, where A is of size, say I'm taking a general matrix M by N. If M is equal to N, A is invertible, of course, several methods exist. Many numerical schemes are also available to get the solution of that matrix equation. Anyway, that is not very interesting situation. Okay. So on the one hand, I can have the case where m is bigger than n. Okay. So meaning that this system is essentially overdetermined. So in general, it doesn't admit any solution. In such a case, as I told you already, what we try to do, we try to find an approximate solution. So we try to find alpha in such a way that the distance between a alpha and y is minimized. So that is essentially going to be the approximate solution of the matrix equation in the case where m is bigger than, row size is bigger than column size. This is of course the problem of scarcity. When I say problem of scarcity, I mean to say that the system doesn't have any solution, but I am settling for approximate solution. Okay, so this is of course not very interesting from the point of view of research. Of course, it has its own applications in some domain. Okay, but in CT setting or in the tomography setting, this is not a very interesting scenario. Look at the other scenario. The other scenario is the case where m is smaller than n, which means row size is smaller than column size. Okay, so from simple or from elementary results in matrix theory, we know that system y is equal to ax in this particular case admits infinitely many solutions, right? So imagine, as I told you already, two equations in space, which means two planes in space. Those two planes actually intersect at infinitely many points. Of course, if they are not parallel, those two planes are not parallel, they will intersect at infinitely many points, which means the system has infinitely many solutions. So if I have two planes which are non-parallel, so they will intersect at infinitely many points, meaning that if you convert them in the matrix form y is equal to ax, the system has infinitely many solutions. So this is the case. This is in a way the problem of plenty. The scenario is a kind of problem of plenty, and of course this will give us plenty of problems, which we will see. So the matrix A is referred to as a dictionary in this case. In y is equal to ax, A is referred to as a dictionary. Why the word dictionary? Reason is that if you look at y is equal to ax, what is it that we are doing? We are writing y as a linear combination of columns of the matrix, right? So the y is described in terms of essentially columns of the matrix. So the description of y can be, or the properties of y can be inferred from the columns of the columns actually that have significant contribution in the linear combination, right? But I repeat, suppose my solution is sparse. Okay, very few components are non-zero. Okay, then what happens? Take for simplicity in y is equal to ax, the very first component in x is non-zero, rest of them are zero, which means the first component is x1, which means y is equal to x1 into the first column, right? Which means y essentially has only the properties of the first column. Suppose for illustration purpose, in y is equal to ax, in x, the first two components are non-zero, which means y is equal to x1 into the first column a1 plus x2 into second column a2, which means the two columns a1 and a2 are giving description of the vector y. So what are the two properties the columns a1 and a2 have? Okay, from that one can in fact infer the properties of this vector y. Okay, so this is again another importance of this sparse solution. You look at essentially the components, the non-zero components in the solution, which are actually contributing to the representation of y. Then based on that, you can infer some properties of the vector y. This has actually far-reaching applications in image processing. In that sense, actually, the matrix A is called a dictionary. Okay, so as I stated already, in the underdetermined setting, the system y is equal to ax has infinitely many solutions, right? So when there are infinitely many solutions, one can in fact impose several criteria. Okay, and of course one can see that each and every criterion will give rise to a solution having certain properties. So one such criterion can be smallest solution. You pick the solution that lies close to origin. I am repeating, the matrix equation Ax is equal to y has infinitely many solutions. When m is smaller than, row size is smaller than column size in general. Okay, so one of the ways of obtaining solution is to pick the solution that lies close to origin, which can be actually posed in the form of an optimization problem like this. Among all solutions, you pick the fellow for which actually distance from origin is minimum, which is nothing other than minimizing 2 norm of the vector. 2 norm of vector is nothing other than the distance from origin. Okay, so when you solve this optimization problem using simple Lagrange multipliers approach, we end up getting this as the solution, right? This is of course one solution, but please note that this solution actually won't fit in our CT application. Why it won't fit in? Reason is that in general, this X tilde is a dense solution. What I mean to say here is that in general, all components in X tilde can be non-zero. But look at CT application. In the CT application, we have seen the need for a solution wherein very few components are non-zero. So the smallest distance solution will not give rise to a solution. Smallest distance condition will not give rise to a solution that is meaningful and that will fit in our requirement, tomography application. Okay, it has its application in some domain, but it is not very useful when it comes to the reconstruction problem in tomography. Okay, but what is our requirement? As I stated already, our requirement is to find the solution wherein very few components are non-zero. Okay, I am defining that. Suppose 0 norm alpha is a count for number of, sorry, this should be alpha A here, it's a typo. So 0 norm alpha should stand for, suppose this stands for number of non-zero components in the vector alpha. So what is it that I have to do now to get a sparse solution? I have to essentially minimize this number. Pick the solution of this matrix equation subject to this condition. Simple optimization problem. But unfortunately, the way actually what are the Lagrange multiplier method that we applied in the earlier case won't work here. The reason is that this is 2 norm, the distance, Euclidean distance is very nice function. Mathematically speaking, this is a differentiable function. Okay, but 0 norm on the other hand is a very bad function. This is not even a norm. It doesn't satisfy norm properties. This is just merely a number. Of course, this is also a number, but this is a nice function of alpha. But this is a very bad function of alpha. So the earlier technique, which is Lagrange multipliers approach, won't work in this case. Right. Secondly, in more technical terms, this is not a convex optimization problem. The 2 norm is a convex function. This is not a convex optimization problem. This is in fact NP-hard. In the sense that as the size of the matrix increases, the complexity involved in finding the solution of this optimization problem actually grows exponentially. Okay, but we have already seen that in tomography application, the size of the matrix runs into millions. Okay, so we need to have a smarter way to get the solution of this matrix equation. That smarter way is mathematicians have attempted. They came out with some nice results, which actually say that in place of this 0 norm, you take 1 norm. You solve this optimization problem. So I have a different problem. Instead of solving this problem, I am solving this problem. There is a theory just saying that under some nice technical conditions on A, these two problems actually give rise to same solution. So I can solve this problem, then I can find the solution wherein very few components will be non-zero. Let us look at the geometrical interpretation. 2 norm minimization is what? Imagine you are in the XY plane. Okay, XY plane, you have one equation involving two unknowns. I have only one equation. So minimizing distance condition essentially will give rise to a point like this. Distance 2 norm of a vector being constant is equal to what? It is a kind of circle in 2-dimension case. So as you keep increasing this radius of the circle, that will hit the plane at the line at one point. At that point, both components x1 and x2 can be non-zero, which is a dense solution. But I am not interested in solution. So in 2-dimension case, when I look for sparse solution, I essentially look for the solution wherein at least one, wherein one component is non-zero. Right? So the one component being non-zero is either this vertex or this vertex. So 1 norm of a function essentially gives you this kind of diamond. So solving this optimization problem will give rise to one of the vertices, which is essentially a sparse solution. I mean to say that one of the components is 0. If this is the solution, then the x component is 0. If this is the solution, then y component is 0. So this is what I am interested in. A question now arises: under what conditions do these two problems give rise to same solution? I am not going to the details of it. So there is something called restricted isometry property. Under very technical conditions on A, the two problems actually admit same solution. Of course, several groups developed software, one group at Stanford, one group at University of British Columbia. Of course, I was a part of this group when I was a postdoc in Canada, developed software. That software can be used to solve this optimization problem. Fine. Now, let me repeat. What is it that I have covered so far? I started with application in tomography. Then I converted that in the form of a matrix equation. Then I realized that there is some property that is naturally present in the image that is to be recovered. Okay, so that property is what? Sparsity of the solution. When I say sparsity, I mean to say that in the matrix equation y is equal to ax, many components in x are non-zero, zero, or very few components are non-zero. So when I solve this equation y is equal to ax, essentially for sparse solution, okay, then that solution can be seen to be useful in medical domain. Okay, now I'll come back to tomography. Then once I complete tomography, I'll move towards machine learning, the mathematics behind machine learning, which is the second part of my presentation. So already I have stated that y is equal to ax. In y is equal to ax matrix equation in tomography, the matrix A is given by discrete Radan transform matrix. Okay, when I say discrete Radan transform, we have seen that grid rays actually passing through that grid. We've generated a matrix whose elements are zeros and ones, either 0 or 1. So now task is to essentially obtain x by inverting this matrix equation y is equal to ax. Okay, for sparse solution. For low-dose tomography, obviously the row size of the matrix or the size of this vector is which is m, which is smaller compared to column size. Okay, so obviously what happens, this A becomes fat and short matrix. So this is actually automatically, naturally getting reduced to underdetermined system. In fact, there are other mathematical issues here. The Radan transform, the matrix A that is given by Radan transform, actually in general has very poor properties. I told you under very technical conditions, one norm problem gives rise to sparse solution. But unfortunately, this matrix doesn't satisfy all those properties. So what we attempted to do, we actually tried to improve upon the properties of this matrix by considering some optimization problem. Okay, then when we improved the properties, then we ended up noticing that you see here, suppose I give say 1/3 of the measurements. Okay, if I use original matrix as such, I get actually this kind of image. See here, again, if I actually improve the properties of the matrix, then what I get is essentially this one, which means essentially I have the data. Okay, I'm not asking for extra data. I'm trying to manipulate data in such a way that the reconstruction becomes good. Okay, how that manipulation is done? Through some optimization technique. Okay, we improve the properties of the underlying matrix using some optimization techniques. Then we noticed that the quality of reconstruction actually will become good. Here, of course, we considered some other set of samples, reconstruction here, and this is the improvement we obtained. Okay, this is of course we increased the number of samples here. Compared to this, we considered more number of samples, and compared to second row, we considered more number of samples here. You see that here, just a simple mathematical treatment is resulting in the image of very good quality, right? So this way, the application that comes from medical domain can be dealt with using mathematical techniques, and in fact, we can show the promise. Promise in the sense that patient can be given lesser doses. At the same time, there is no compromise on the quality of the reconstruction. So this is one application there where one can see the deployment of the techniques from linear algebra and optimization theory. So let me now move to the second part of this is of course another reconstruction. So reconstruction quality is very bad here, as you can see. So when we actually improve the properties of the matrix using optimization techniques, it's relatively become good. We increase the number of X-ray projections here. This is becoming good here. If with the original set of measurements, this is the reconstruction. With improved properties for the matrix, and this is the reconstruction quality. Just purely mathematical treatment. Okay, that is giving us an image of good quality. So what is it that we have done here? Nothing other than the techniques from linear algebra and optimization theory. Okay, now let us actually move to the second part of my presentation, which is about the mathematics behind machine learning. Okay, so the whole objective behind this is to again demonstrate that the methods from linear algebra and optimization theory have actually a vital role even in domains like machine learning. Okay, that is the whole objective of my presentation. Let us see, we all know artificial intelligence is a trending area now, and machine learning is also a trending area. So AI essentially refers to the science of mimicking human beings. Okay, it is like basically making a system think and work like a human being. Whereas machine learning is a sub area in artificial intelligence where machines are actually trained, we have some data. Using that data, a machine is trained to behave like a human being. Okay, that is it. So in AI, essentially, you don't have any data. Okay, but we expect, or we train the system, not training here, we expect the system to behave like a human being. Whereas in machine learning, you have some area, you have some data, and using that data, we train the machine in such a way that the machine actually thinks or works like a human being. Let us look at one application. See, every day we use YouTube. Okay, we play actually several clips on YouTube. Suppose I am the person who plays actually say some devotional songs right in the morning between 6 and 7. Okay, so the moment I log into my account, YouTube actually shows me some clips, right, of devotional songs. Suppose I am a person who actually watches news say around 9:30 in the morning. So the moment I actually log into my account, obviously YouTube actually shows me the relevant clips, the clips related to news. Okay, suppose my kids actually watch cartoon kind of programs around 4 o'clock. So the moment we log into YouTube around 4 o'clock, it will show actually the clips actually pertaining to cartoons. So suppose actually I continue with this practice, say for example, some period, say 1 month or 20 days. So after that, automatically YouTube actually shows the relevant clips, which means there is some learning pattern. Okay, so there is some algorithm running behind that. Okay, and that algorithm actually learns our search pattern. Oh, this guy is actually searching for devotional songs. This guy is searching for news. This guy is actually searching for, say, some cartoon kind of programs around 4 o'clock. So YouTube actually learns my searching pattern. Based on that, automatically it will start showing relevant clips, which means there is some data. Okay, based on that data, system is learning. Okay, machine learning is all about that. This is one simple application. Now, actually, let us look at application that comes from medical domain. So that application is something like this. Suppose this is normal ECG signal. Okay, we all know basically this actually gives you the picture of the heart functionality. Suppose this is abnormal ECG signal. This is also abnormal ECG signal of another type, abnormal ECG signal of other type. Okay, on looking at perfectly normal signal or perfectly abnormal signal, doctors actually can say if it is normal signal or abnormal signal. Suppose there is a slight deviation from normal behavior. Okay, if there is slight deviation, sometimes we may not be able to notice that. Our naked eye actually will not be able to provide that information about that deviation from normal behavior. On the other hand, if I train a system saying that this is normal ECG signal, this is also normal ECG signal, this is also normal ECG signal, this is abnormal ECG signal, this is abnormal ECG signal. Suppose I train my system like that, providing some data samples. Automatically, whenever you give new signal, it will say if it is normal signal or abnormal signal. Okay, this is essentially the learning. Let's look at some examples. This is of course one application. I'll come back to this application down the line. Let us look at another a couple of examples of learning. One example is children learning alphabets, right? So normally what happens? We teach a child to recognize A. We write A on the board. We ask the child to say A. Okay, when we write when we write A on board a couple of times, there could be small deviations. One A can be like this, the other A can be like this, the other A can be like this, fourth A can be like this. So this way actually one can write the A in several ways. But each and every time we write A, we ask the child to say this is A, this is A, this is A, this is A. Similarly, we ask the child to say this is B, this is B, this is B, this is B, like that. Similarly, this is C, this is C, this is C. So what is happening in this process? The child is learning. The child actually learns that whenever a pattern has this kind of structure, okay, this is A. Even if there is small deviation, child will automatically recognize. Similarly, B, similarly C. This is essentially learning. The other example of learning could be the spam filtering of emails. So spam filtering of emails, what essentially happen? Whenever there is an email with so and so words, presence of so and so words like, for example, you have won lottery. Okay, say $1 million lottery. You give us your account details, we'll transmit money to this, something. We all know we get several notorious mails. Okay, the presence of certain words in the body matter of the email signifies that that mail is spam, right? Similarly, there can be many such mails. Okay, so what actually system does? System actually learns. Okay, if these words are present, this is a spam mail. We essentially what happens? We supply several mails to the system, saying that this is the mail having so and so word counts, lottery, $1 million, your account details, all that. Similarly, some other mail. Okay, so and so words are present. So we tell the system if these words are present, this is spam. If these words are present, this is spam. If these words are present, this is spam. So that way, actually, what happens? We train a system, we come out with an algorithm. Whenever we give new mail to the system or the words that are present in the mail to the system will say if it is a spam or not. So this is essentially what learning. Okay, so learning is what now? As I stated here, Learning is essentially the process of converting experience into expertise. Suppose I want to say develop. Say suppose I want to see in order to believe in some person. Okay, what we normally do, we look at the past instances. Okay, we try to ascertain whether the person is trustworthy or whether the person is say reliable or whether the person actually completes the task given to him. Okay, we develop some impression about the person, keeping certain experiences in mind. So what is it that we are doing in this process? So we are trying to come out with a decision making rule based on the experience we have with that person. This is exactly learning. So learning is essentially the process of converting experience into expertise. So in the language of machine learning, this expertise is what? A kind of decision making rule. Okay, let us see now how the decision making rule can be obtained given data. So in ML, essentially there are several issues. One is scalability, the other is stability, the third issue is complexity. Let us see actually what these issues mean. So when I say scalability, I mean to say this. Look at this spam mail example. Suppose I have, say, for example, 100 words. Okay, in the first mail, so and so words are present. In second mail, so and so words are present. As long as I have small set of mails, I can memorize words. Suppose, say, for example, I have 10,000 mails. So beyond some point, I cannot memorize the words in order to flag if the given mail is spam, right? So obviously, what happened that so things actually will go beyond our capacity. We cannot memorize things. Similarly, when you train an algorithm, if the algorithm works on smaller data set and if it collapses when you supply a larger data set to the algorithm, then the algorithm is said to be not scalable. On the other hand, if the algorithm works very well, even on larger data set, then it is said to be scalable. So scalability is one important issue when it comes to designing machine learning algorithm. The second important issue is stability. So when I say stability, I mean to say this. Of course, I am giving this definition in very loose sense, not in precise mathematical terms. When I say stability, I mean to say this. Suppose in one of the mails, I have the word account. I know the moment actually the word account is there or lottery is there, I know that is a spam mail. Okay, sometimes suppose in that particular mail, the word account is misspelled as ACOUNT instead of ACCOUNT. So then what happened? A human being immediately can say that, okay, this word is misspelled. Okay, but you cannot expect the system to behave like a human all the time. Okay, but suppose even if the word is something like ACOUNT instead of ACCOUNT, if the system is able to recognize that, then we say that the algorithm is stable. Because there is minor error in the data input. In spite of that, if the algorithm works well, then the algorithm is said to be stable. So when we design algorithms, this is of course one practical issue that one has to keep in mind. So stability is also an important issue. The third issue is with the complexity. Complexity is all about what? Suppose you design an algorithm. Okay, if that algorithm takes 1 week to give you result, then what is the use of that? Right? We expect the algorithm to give us result in almost no time. Google search, for example, you see, as I told you, it is eigenvalue problem. Okay, so the underlying matrix, the size of the underlying matrix runs into millions. But despite that, Google actually finds eigenvalue, dominating eigenvalue in almost no time, which means there is efficient algorithm, right? So we expect the algorithm to give us result in almost no time. In other words, the complexity associated with the algorithm, number of floating point operations associated with the algorithm should be small. If algorithm actually has smaller floating point operations, we say that it has a lesser complexity. So for all practical reasons, scalability, stability, and complexity play actually a vital role in machine learning. So these are the issues. Now let us take a look at the types of learning. We looked at several examples of learning. Several applications of learning. The spam filtering of emails is one application. Okay. Children's learning alphabets, of course, that is general application. So similarly, ECG signals, that is of course real life domain. You give bunch of ECG signals to algorithm. The algorithm actually will learn the trend in the signals. Then whenever you give a new signal, it will identify if it is normal ECG signal or abnormal ECG signal. Okay, so there is a learning process. So broadly, there are two types of learning. One is called supervised learning. The other is called unsupervised learning. What is the difference? Learning in the presence of teacher is what is called supervised. Okay, in other words, look at, for example, alphabets example. A child learning alphabets. In that example, we are writing and asking the child to say A. Similarly, we write B and ask the child to say B. So there is a teacher, right? In other words, in simple terms, there is a kind of label data. So what are the character A we write on board? Okay, that is actually coming with a kind of label. Similarly, look at ECG signals. We are telling the system that, okay, this is normal signal, this is normal signal, this is abnormal signal, this is abnormal signal, which means a given signal is coming with a label, normal or abnormal. Okay, so if learning is done using data with the labels, then it's called supervised learning. Okay, suppose you have only data. You don't know if a given data vector is normal or abnormal. You have no information about that. Then this is what is called unsupervised learning. So learning without the presence of teacher is what is called unsupervised. Okay, so I'm going to talk about two examples, a couple of examples that come under each supervised category or unsupervised category. So input to all learning algorithms is what? Training data. For us, mathematically, data means what? Set of vectors. So be it the application image processing, or be it the application pattern recognition, be it the application healthcare domain, ultimately what happens, whatever the data we have at hand, that is actually converted in the form of vectors. Okay, now once actually we have everything in the form of vector, that's purely mathematical problem. Okay, so that is where actually we try to bring the ideas from machine learning and come out with a decision making rule. So input to all learning algorithms is training data. The data can be with labels or without labels. Okay, now let us look at some of the issues in machine learning. One major issue in machine learning is with the size of the data. What is the meaning of that? Look at, for example, again, some applications. I have some medical images. Some of them actually correspond to skull. Some of them correspond to hand. Some of them correspond to lung. Some of them correspond to chest, so on and so forth. Okay, now, as I told you already, in medical domain, oftentimes we take image of very huge size. It can be 5112 by 5112 or 1024 by 1024. When you vectorize this image, obviously the number of components in that image will be too huge. Okay, oftentimes it can be about 10 lakhs. It can be 1 million. Okay, so when you vectorize that, and if you try to play with those vectors as such, you run into problems, right? Again, all these problems arise, like for example, finding eigenvalues, solving matrix equation, these problems arise. So in order to deal with the huge images, what one tries to do, one tries to reduce the size of the data. Okay, what is the way to do this? So the way of reduction of the size is what is called dimensionality reduction. The process of reducing the size of the vector is referred to as the dimensionality reduction. So look at again this particular application. I don't remember the size exactly. I think some 327 by 327 something. So which is some big number. When you vectorize this, I think some 12,000 or 30,000 components are there. Suppose we have say some 1,000 such images. When you vectorize each and everything, so I have essentially 1,000 vectors where each is of size around 13,000 or 14,000. Huge data. Okay, so now I have to reduce the size of each vector of size around 10,000, around 13,000 or 14,000 to a very small number. Small number can be maybe 100 or 200 in such a way that when I reduce the size, I should not lose major properties of the image. So in mathematical terms, I have a vector in very high dimension space. That vector is actually coming from skull or a hand or chest or lung or whatever it is. Okay, so I would like to project this into a lower dimension space in such a way that the properties actually, the major properties of the vectors in higher dimension space will remain intact even in the lower dimension space. What is the meaning of it? Meaning is, say, look at all skull images. Okay, when you look at skull images, when you vectorize all these images, so as I told you already, an image is a matrix. Okay, say for example, n by n matrix. So out of this n by n matrix, one can have a vector of size n square by 1. In some way, you take all first row elements first, then all second row elements next. That way, actually, one can generate a vector out of a given matrix. Okay, now all these skull images actually give rise to some bunch of vectors in the very high dimension space. Similarly, all hand images will give rise to vectors in the high dimension space. In the very high dimension space, they are in fact clustered in the sense that all skull images actually can be seen as points at one place. All hand images can be seen as points at some other place. So because of the natural properties that are there in this image, you can see a kind of grouping in the higher dimension space. Okay, when I project data to a lower dimension space, I expect this grouping to happen in the sense that all skull images should be seen at one place, all hand images should be seen at another place, all lung images should be seen at another place. It should not be that they remain mixed in the lower dimension space. If that is the case, then the whole purpose of dimensionality reduction actually has no value. Okay, so the dimensionality reduction basically is about projecting data to a lower dimension space in such a way that even in the lower dimension space, the topology of the data points remains same. When I say topology, I mean to say that what are the properties that I have in the higher dimension space? Example, grouping. Okay, that should remain same even in the lower dimension space. So in such a way, I have to project data to lower dimension space. Okay, this is what is called dimensionality reduction. Normally, people do this in a couple of ways. One is about projecting data to lower dimension space. The other is about extracting some of the properties of the features. In other words, a property from the images. Look at actually what this feature means. In the skull images, I have a kind of bowl-like pattern. You see, there is a kind of bowl-like pattern in skull images. Similarly, if you see lung images, I see a kind of, I see some other property here. Loosely speaking, a kind of texture property. If you see hand images, there is a kind of piecewise constant behavior. Okay, so in other words, the image is actually coming from one particular department, like for example, radiology have certain properties. The images that come from dermatology department, skin images, have some properties. Okay, so if I keep those properties in mind and extract, generate a shorter representation of vectors, then that is what is called feature extraction. So feature extraction is all about looking at the properties of the image carefully and then projecting data to lower dimension space in some way. Then this is what is called feature extraction. But dimensionality reduction is basically the wording given in very broad sense. Let us see how dimensionality reduction is achieved or projection of data to lower dimension space is realized. So this can be done like this. There is something called principal component analysis or singular value decomposition. Okay, using which actually one can have the projection of data to lower dimension space. Look at this. Let us see actually what SVD stands for. Suppose I have a matrix of size m by n. Okay, in SVD we try to find two matrices U and V and a diagonal matrix D such that A is equal to U into D into V transpose holes. Which means this matrix A is written as product of three matrices having certain properties. What are those properties? U and V are unitary matrices or orthogonal matrices. D is a diagonal matrix. Okay, so now what is the beauty of this technique? The beauty is that if the rank of the matrix is very, very small, obviously rank of the matrix is smaller than minimum of m and n, then what happens? In A, essentially you have mn number of elements because A is of size m by n. Mn number of elements, whereas if you look at the number of distinct elements in three matrices, which is essentially m plus n plus 1 into r. Okay, simple verification, nothing big about it, which means mn number of elements are converted in the form of m plus n plus 1 into r number of elements. If r is very, very small, m plus n plus 1 into r is very small compared to mn. So in this process, I am not losing any information. The gain that I have obtained is mn, a vector in the space of dimension mn is converted in the form of a vector whose dimension is m plus n plus 1 into r. Let us take a look at this particular example. I have taken my image, which is of size 363 by 356. I think roughly about 13,000. This matrix is of size 363 by 356. So this matrix has around 13,000 elements. So what I did here, I considered this factorization, matrix factorization along the diagonal. The elements of the diagonal are essentially what? The eigenvalues of the matrix A into A transpose or A transpose into A, which are essentially singular values of the matrix A. So what I did essentially, I retained those eigenvalues whose magnitude is above 1, which means there are about 321 eigenvalues out of 356 eigenvalues whose magnitude is above 1. Again, I multiply all three matrices. Then I get this image, which is almost exactly, not exactly, almost like my original image. Here, what I did essentially, along the diagonal of this main matrix, I considered only 5 eigenvalues. Okay, I considered 0 in place of the remaining eigenvalues, I multiplied. So essentially, whatever the new A that I get, okay, will give rise to this kind of image, which is very bad compared to this. When I consider 10 eigenvalues, I get this one, which is slightly better than this. When I consider 15 non-zero entries on the diagonal of this matrix, I get something which is better than this one. So as I keep taking more and more number of elements on the diagonal of the middle matrix D, I keep actually getting better better reconstruction quality. Okay, now this is a trade-off. Trade-off in the sense that I can fix the error. Suppose new matrix that I get is say A tilde, I can fix the error. Accordingly, I can take actually some number of elements on the diagonal. So then what happens now? Which means I'm basically taking low rank approximation of this matrix. When I take a low rank approximation for that particular rank, the number of entries in the right hand matrix is essentially m plus n plus 1 into r, which is very, very small in general compared to the number n into n. This is essentially dimensionality reduction. To repeat, dimensionality reduction is all about projecting data to lower dimension space. Okay, in such a way that there is no significant loss of information between the original vector and the vector in the lower dimension space. No, of course, in terms of properties. Okay, this is one dimensionality reduction. Look at the other dimensionality reduction. Of course, there are several methods available in the literature. This is one most elementary method, which is based on simple mathematical ideas. Of course, this method is linear in nature. Linear in the sense that I have a vector in the higher dimension space. Suppose that vector is A, X. Then I am finding a matrix because this is linear. Suppose that matrix is B, capital B. Then suppose my vector in the lower dimension space is Y. Then Y is essentially B into X because this is linear projection. Okay, so now this linear projection works as long as there is linear duplication among the components. What is the meaning of it? Meaning is that suppose my vector, as long as the components in my vector X are like this, x1, x2, 2x1, 3x2, x1 plus x2 like this, which means many components are linearly dependent on some of the components. If this is indeed the case, the technique like singular value decomposition works very well. On the other hand, if the components in X are non-linearly related, then SVD doesn't work. Like for example, the components are x1, second component is x2, third component is x1 into x2, fourth component is x1 square, then SVD doesn't work. Okay, so in order to actually have dimensionality reduction, even in such cases, people came out with several methods. So one such a non-linear dimensionality reduction is manifold learning. What we try to do here, see, if you look at singular value decomposition, we did not make use of the properties of the underlying vector. But here actually one can make use of the properties of the underlying vector. Okay, of course, there is a beautiful mathematics behind it. So we assume that whatever the data points we have, like for example, I'll show you some images here. Look at these images. Okay, I have several images where in some of the cases the person is laughing. In some of the cases the person has serious face. Okay, in some of the cases the person has a puzzling face. In some of the cases the person has pensive mood. Like this, the person can be seen with several moods. Okay, for some reason, suppose I want to identify the mood of the person, right? This is my application. For some security reason or for some reason, I want to identify the mood of the person. Then in this particular what one can notice here, if you vectorize all these images, see, these are all images of the same person. When you vectorize all these images, you can see that the person with the laughing faces can be seen at one place. Because when the person laughs, normally you can see changes pertaining to this lip area. When the person has some other moods, for example, surprising face, the changes in the image can be seen in the forehead area predominantly. Okay, so because of this, what happens? All these, when you vectorize these, they actually, it can be seen that they approximately satisfy manifold pattern. Manifold, when I say manifold, I mean to say this. As an example, I am saying all laughing images can fall in this particular patch. This is of course very loose way of conveying the concept. Mathematically, this is not correct, but to make you understand, I am just giving this example. Okay, so all laughing images can be seen in this blue area. All images wherein the person with serious face will fall in, say, for example, yellow area. Like this, on the whole, because of local changes in the images, on the whole, we can expect that the vectors actually describe a kind of manifold, at least in the sense of approximation. So there is some underlying property or signature present in such images. If that is indeed the case, we can project the data points. Here, of course, this is in simple 3-dimension case. All our data points are in 3-dimension space. They are actually projected to 2-dimension space. See here, What are the points I have here pertaining to this blue patch? They are all actually at this particular place. Similarly, all points that I have in the similar blue portion, but at a different place, they are actually falling in this patch. Similarly, yellow points actually are seen actually at one place. Pink points actually can be seen at one place. Blue points actually can be seen at one place. So what are the, if you take a point here, what are the neighborhoods actually that point has? All those points actually can be seen here. A point and its neighborhood can be seen at one place, even in the lower dimension space, which means the topology is preserved here. Okay, I'm not losing. So because this is what I expect when I project data to lower dimension space, what are the broad property that I have in higher dimension space? I expect that to remain true even in the lower dimension space. So when data points actually describe this kind of property, then it is said to be a manifold. So mathematically, a manifold is a topological space wherein on a smaller scale, the points actually behave like an Euclidean space. Okay, I don't want to go into the details here, but a mathematical concept actually plays out here. Let us see now, if the data points actually satisfy, for example, this S kind of structure, how the projection to lower dimension space can be done. The projection to lower dimension space can be done by using some optimization problem. It is in fact posed as an optimization problem. How this is done? It's just a simple idea. Take, for example, a point in this blue patch. Okay, if you look at all points, blue points having similar color, okay, they actually lie on a plane. Now what try to do, take a point and try to represent that point linearly in terms of its neighbors. Similarly, try to represent a point falling in this yellow patch in terms of its neighbors. So this typical ith point is represented as its in terms of its neighbors. Now when you find these weights in such a way that the distance between these two is minimized. Now do this for all points, actually minimize the error. So when you solve this optimization, find weights in such a way that the total error is minimized. This is simple optimization. This is simple convex optimization problem. When you solve this, we can essentially have expression for the weights. Now what we try to do, using these weights, we try to obtain the points yi in the lower dimension space. What is yi here? Yi is the image of the point xi in the lower dimension space. Of course, the mapping is non-linear here. So what is the property that we keep in mind while finding yi? Whatever the neighbors a point has, okay, the same neighbors actually are expected to be present even in the lower dimension space, which means structurally we consider the same optimization problem except for some difference, which is taking yi in place of xi. Now weights are known in the second case. By solving this minimization problem, we obtain yi. Okay, so the yi are essentially the points in the lower dimension space. This is what those are the points that we are interested in. See, nothing here. Simple matrix. In fact, when you expand this optimization problem, we can see that this will again lead to solving matrix equation. This will again lead to solving eigenvalues of the problem. So I have an application that is coming from real domain. So we have posed that in the form of an optimization problem, and then we use actually ideas from numerical analysis, linear algebra, optimization techniques, and basically arrive at a meaningful solution. So this way the data from higher dimension space can be projected to a lower dimension space. This is one simple application of this. You take all facial images. So you vectorize all those images. Okay, apply this projection to simple 2-dimension. See, this is long vector in very high dimension space. When all these images are projected to lower dimension space, which means literally we are losing all properties. See, imagine you have a vector of size, say for example 10,000. That is projected to a 2-dimension space. Obviously, we tend to lose a lot of properties. Despite that, all smiling faces, that vectors in 2-dimension space corresponding to smiling faces can be seen at one place. The vectors actually corresponding to some other category, okay, can be seen at one place. So this way, actually, they are actually clustered in the 2-dimension space. Okay, so this property is actually remaining true. What are the broad property that I have? That broad property is what in the form of laughing or crying or seriousness or something else. Okay, that property is actually remaining true even in the lower dimension space also. So to repeat, the projection of data to lower dimension space, it is what is called dimensionality reduction. There are several methods. I talked about 2 methods. Okay, one is actually giving rise to the projection, which is linear. The other is giving rise to a projection to a lower dimension space via some nonlinear mapping. This is what is called manifold learning. Okay, so of course I have several issues in machine learning. The first issue is about dimensionality reduction, which is all about projecting data to lower dimension space. Now, once you are in lower dimension space, our objective will be to what? Objective will be to group, right? See, application can be what? I am giving a new image. My objective is to see whether the person has a crying face or laughing face or the face with some other feature. Then what I try to do now? To begin with, I project the data to lower dimension space. Of course, not to do in practical terms. Okay, if the initial dimension is normally 10,000 or 15,000, we project it to a dimension say 100 or 150 like that normally in application. Now, whenever I have a new image, whenever my task is to identify the person's actually mood, what I try to do, even I project this also to lower dimension space. Then what I try to do, I have clusters in the lower dimension space. So I try to see whether the given image is close to this cluster or that cluster or some other cluster. So based on the proximity of the image, okay, what I do, I determine it's a cluster. So based on the cluster, I say whether the person is crying or laughing. Okay, now for this, the next task is what? Clustering of the images or grouping of the images in the lower dimension space. So first thing first, to begin with, we have data in very high dimension space. Then we project it to lower dimension space. So in the lower dimension space, now our activity is completely in lower dimension space. Okay, so in lower dimension space, actually we group data. Okay, grouping data means, look at, for example, YouTube application. So between 6 and 7 o'clock, okay, this person is searching for religious songs. Okay, between say 9 and 10, this person is actually searching for video clips actually related to news. Between 4 and 5, this person is searching for video clips related to cartoon kind of programs. So that way, actually, some grouping is achieved. Okay, so the timestamp is giving you the property of the cluster or group here. So similarly here, based on the cluster, actually, we decide the properties of the properties that are present in the image. Okay, which is our objective, the property that is to be identified. Okay, so once we are in lower dimension space, our task is what? Our task is to cluster or group images, group the vectors in the lower dimension space. This grouping, in fact, can be done in two ways, as I told you already. One is what? Supervised, the other is unsupervised. Unsupervised is what? Look at, for example, alphabets A, B. Okay, so when you expect the system, say in document processing, we have images corresponding to all several A images. We extract the properties. We give all those now. All those actually are essentially vectors in the form of vectors. We give the vectors corresponding to several A's to system. Similarly, we give vectors corresponding to the character B to the system. We give vectors corresponding to the character to C to the system like this. Whenever we give vector to the system will identify whether it is A or B or C or D or any other character. Okay, so once actually we project data to lower dimension space, to begin with, you have to have grouping. Okay, that grouping is essentially what? In supervisory fashion or unsupervised fashion. So I am now going to talk about how this grouping is done in an unsupervised fashion to begin with. So unsupervised method, under unsupervised fashion, there are again several ways, several methods. One simple method is what is called the K-means algorithm. Let us try to understand the mathematics behind K-means algorithm. So to begin with, I have data points xi, which belong to some dimension space. Okay. Now our task is to what? Obtain several groups, several subsets of this set in such a way that all vectors belonging to a particular subset, say Sj, have one property. All vectors belonging to another subset, say S2, okay, have another property. All vectors belonging to another set S3 have one property. Like that, actually, I want to find the groups. How this is done? This grouping is done again by solving this simple optimization problem. Nothing else. It is based on common sense. Okay, when you solve this optimization problem, what we get are essentially the sets S1, S2, S3, so on, Sk, whatever it is. So look at that medical domain application. Suppose I have several images. I'm going to talk about one application here. Look at this example. So I have taken 25 medical images. These are actually brain images. These are lung images. These are hand images. These actually correspond to some other category. So from every category, I have taken 5 images. In total, for simplicity, I have taken 25 images. When I run K-means algorithm, I expect the first group to contain all these. I expect all these 5 images to fall in one basket. I expect all these 5 to fall in another basket. Similarly, I expect all these last 5 in another basket. When I run K-means algorithm, I get this kind of grouping. See, all these 5 members are actually falling in the first basket, but there are 2 wrong members. Okay, these 3 are actually falling in second basket, but 2 members are missing. I have 2 extra members which are wrong, but this is of course correct, but 2 members are absent here. These first 4 are correct, first 5 are correct. Okay, the third group is correct, but with 1 wrong member. Fourth group is correct, but 1 member missing. Why this is happening? This is all because of the distance function that we use. By the way, how this is done? What is the idea behind this k-means algorithm? Let us see this. To begin with, I have say 25 images. What we try to do, we vectorize all these images. Then we project these to lower dimension space. Now I am in lower dimension space. Once I am in lower dimension space, I have 25 images. To begin with, what I do, I take arbitrary grouping. You just define the set S1 to be, you pick actually some 5 members and put them in the set S1. Okay, of course, this is not a correct grouping. Pick another 5 members and actually put them in the second set S2. Pick another 5 members and put them in set S3. Pick another members and put them in the set 4. So I know essentially K. K is here 4 because I have taken 5 images from 4 categories. So K is equal to 4 here. So to begin with, I basically consider 4 subset arbitrarily. Now what I do, I take the average of the members actually of the first set. I take the average of the members of the second set. I do this for third and fourth sets also. Now I have actually 4 centroids or 4 average vectors. I have 4 vectors now, which account for averages of each basket. Now what I do now, I find the distance of each and every distance of all 25 members from the first vector. So whichever the fellows actually have shorter distance from x1, then I do this. Take for example first image, first vector x1 corresponding to the first image. I find the distance of this vector from these 4 averages. Suppose x1 is close to the second average, then yeah, please.
Sorry for the interruption, sir. There is a small disturbance is there, sir. Your voice is breaking.
From my side, actually, there is nothing, sir. Just please hold on. I'll turn off fan. Yeah. Just sorry for the inconvenience. But is this okay now?
Sir, while you are talking, you are getting, sir.
I don't do that. I don't have anything actually creating noise on my side except for the ceiling fan. I turned off cooler also.
Okay, sir.
Maybe I don't know if desktop is creating problem, but I muted his speaker of this desktop also. Okay.
Okay, sir. Continue.
Okay. Anyway, sorry for inconvenience. So what we try to do now here. So I have picked up actually. I have done grouping arbitrarily. Then for every group I consider the average. Now then what I do, I take each and every member. I see the distance of. I compute the distance of every member from each of these averages. Suppose the first fellow is close to second average. Then I put this first image in the second group. Suppose the third fellow, the second image is close to the first average. Then I put actually third one in the first basket. Like this, basically we refine the groups S1, S2, S3, S4. We keep actually repeating this process. After some point, actually convergence takes place. A question may arise now: why actually convergence takes place? What is the guarantee that there is a convergence? All these issues actually can be addressed mathematically. I'm not going to touch that. So when you solve this, essentially the whole whatever the methodology that I explained can be posed in the form of this optimization problem. When you solve this optimization problem, you essentially end up getting the sets S1, S2, S3, S4, which have basically everywhere S1 contains similar looking images, S2 contains the similar looking images, so on and so forth. Again, the quality of grouping here, as I stated, will depend very much on the choice of the distance function that one takes. Here, of course, as an example, in the execution, while executing this code, I considered Euclidean distance. One can as well take one norm or some other norm. Okay, so different distance functions actually will give rise to groupings having different qualities. Again, the quality of actually grouping can be studied mathematically. I'm not going to touch that here. So this way, a simple fundamental idea from basic mathematics can be used to essentially group the medical images. But nowhere in this process, I made use of the properties of the image. The properties are what? I know there are certain properties, like for example, MRI images, brain images have certain property. Similarly, hand images have certain property. Suppose I keep that in mind. Okay, so while doing this grouping, I can make use of the properties of the images, underlying images. If that is the case, then this grouping is what is called unsupervised. So there is actually one learning mechanism, and that learning mechanism actually goes by the name of support vector machine. So support vector machine is essentially what? Supervised learning. So it's 320 almost. Okay. Support vector machine is supervised learning. Let us see actually how again. So the idea goes here like this. To begin with, I am taking essentially two classes of signals. Say for example, all these blue circles. Okay, they actually, all these blue dots are related to normal ECG signals. All these red dots are related to say abnormal ECG signals. Assume that they are separable. They are separable. So what we try to do now, we try to find a separating hyperplane. Okay, using these data points, I have some label now. The first point, this is normal, 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 this is normal. Suppose this is data point x1, this is data point x2, this is data point x3, this is data point xn. So I give the label. I know all these correspond to normal ECG signal. I give the label say +1. So when for xi, suppose the label yi is equal to +1, then xi refers to normal ECG signal. Similarly, if the label refers to -1, for me understanding is that they are essentially abnormal ECG signal. So I assume here that suppose normal and abnormal ECG signals are well separable in the sense that you can have a separating hyperplane. Okay, on the left side of the plane, you have all normal ECG signals. On the right side of the plane, you have all abnormal ECG signals. Okay, now the problem here, whenever we are given new ECG signal, what we try to do, we try to see if that signal is on the left side of the plane or right side of the plane. So based on where it lies, we conclude if it is normal ECG signal or abnormal ECG signal. Okay, this is plain mathematics, anybody can understand. It's a plain problem that anybody can understand. Now, in fact, the problem of finding a well-defined hyperplane can be posed. Maybe I'll just, the problem of finding a well-defined hyperplane can be posed as an optimization problem like this. When you solve this up, so what is the equation of the plane in general dimension space? Plane is equal to what? X dot to some vector W is equal to some constant lambda. Right, that is the equation of the plane in higher dimension space. So when you solve these, so this W is essentially what? The vector normal to the plane. Okay, so that equation of the plane can be obtained by solving this simple optimization problem. There is some mathematics behind it. I am avoiding that mathematics. So when you solve this, essentially what happens? We end up getting the equation of the plane. Okay, but we have some practical issues here. What are the practical issues? Look at, for example, so these are all these circles refer to abnormal ECG signals. All stars actually refer to normal ECG signal. This is one separating hyperplane. This is also the central red line is also a separating hyperplane. So like this, actually, there can be several separating hyperplanes. The issue is now which one is good, right? Look at this now. When we actually find a separating hyperplane, we try to find it in such a way that these are actually parallel lines. The distance between this line and this line is as maximum as possible. Why this is the case? Sometimes what happens when ECG samples are taken because of some gas problem or some other problem, the person is normal, okay, but his heart function could be slightly different from normal behavior. So because of that slight deviation from normal behavior, though the person has normal pattern, but there can be abnormal, some small changes in the signal, which could signify, which may imply that the signal is essentially abnormal. In other words, in mathematical terms, the signal that is supposed to be on the left side of the plane may fall on the right side of the plane because of error in the measurements. So because of all that, what we try to do when we find a separating hyperplane, we try to find in such a way that this gap is as maximum as possible. When this gap is maximum, even if there is some small error in the measurement, still actually the point actually will fall on the left side only instead of right side. Okay, so this is one requirement that one has to keep in mind. Other requirement is what, again, slightly different problem. Again, you see normal signal, abnormal signals. So this is separating hyperplane. Just one pair. If I were to take these three, this as the separating plane, this point actually P, which is normal, but falling on the right side of the separating plane, which means this is the wrong classification. But the circle, which is supposed to be on the left side of the plane, right side of the plane, but is falling on the left side of the plane. Okay, but if I strictly want all points, all nice normal signals to be on the right side and all abnormal signals, sorry, on the left side and all abnormal signals to be on the right side, then I have to take essentially this line B2. But if I were to take this one, but I would get maximum margin. So what we try to do now, in order to have maximum margin, we allow for some misclassification. Though I know that this is normal point, but I allow this point to be on the right side of the plane. Though this is actually abnormal point, I allow this to be on the left side of the plane. This is again for practical reasons. So, but the gain here is what? Maximum margin compared to what you get here. The algorithm that you get in this case is what is called soft support vector machine. So this word soft refers to essentially allowing some misclassification. This whatever I stated here is what is called hard support vector machine. Okay, I don't allow any point to be wrongly classified here. These are labeled data points. So I have now data points. This xi actually refer to data points. Okay, xi is ith ECG signal whose label is yi, +1 or -1. So the objective is to find this separating hyperplane, which can be solved by solving this optimization problem. And this method actually goes by the name support vector machine. Why this word support vector here? Some of the points actually are falling on this parallel plane, and these vectors, similarly, red points are actually falling on this plane, and these are actually called support vectors, and they play actually some important role. If you look at the mathematics of this, we understand why actually those vectors are important. This is extremely popular classifier, supervisor classifier. Supervisor in the sense that I know basically these are all normal points. I know that these are all abnormal points. I assume that they are actually well separable. Then I can SVM support vector machine is all about finding a separating hyperplane. Once I find separating hyperplane, what is it that we do? Whenever new ECG signal is given to me, I just merely check if it is on the left side of the plane or on the right side of the plane. Okay, again, this is simple mathematical calculation. Then we can conclude if it is normal ECG signal or abnormal ECG signal. Okay, similarly, if this is the class grouping of images, suppose I give information about the images also, then this becomes essentially supervised. Okay, when this becomes supervised, I can incorporate the information of the image into this process. Then basically I can as well have, this is what I stated here is a two-class classification, normal and abnormal. I can as well have multi-class classification. Okay, like these can refer to hand images, these can refer to lung images. You can have some other grouping which may refer to chest images, so on and so forth. So that way we can have several separating hyperplane, and based on that, we can say whether the given image is lung image or a hand image or chest image. Okay, so all this can be done using ideas from simple linear algebra and optimization theory. So one more thing with this, then I'll stop my presentation. So there is something called kernel trick. The kernel trick is what? Suppose our data points are not linearly separable. So far I assumed that the points are linearly separable. It may so happen that, see, all these boxes actually refer to data of one category, say abnormal ECG signal. All these small circles which are lying inside this dotted circles may refer to another category, say normal signals. Okay, but these are not separable by a hyperplane, but they are actually separable by a circle, which means these two classes are separated by a non-linear map. The circle is essentially separating these two classes of points. Okay, one can in fact see that when you see these are essentially in the XY plane, when you project these points into 5-dimensional space via this mapping, then what happens in the 5-dimension, in the space of dimension 5, they are actually separable. One can find a separating hyperplane. Okay, the projection of the data points to higher dimension space so that linear separation can be realized there is what is called kernel trick. Okay, here again several mathematical questions arise. What is the way to project? Who will give us that in 5-dimension space they are separable? That is one question. Second question is, what is this map? This actually won't fall from heaven. We have to be able to find this map. Like this, there are several mathematical problems. So all these problems actually can be addressed using ideas from fields like function analysis, harmonic analysis, linear algebra, optimization theory. So many actually mathematical techniques actually have a very important role to play in machine learning. So there are of course methods like kernel-based learning. I want to actually stop my presentation. Similarly, one can see the application in telecardiology. Okay. In telemedicine, in fact, one can see the deployment of all these ideas. I don't want to actually go into the details of it. I'll stop my presentation here. So let me actually summarize the topics that I covered so far. I started with the title, Numerical Linear Algebra and Applications in Medical Domain. To begin with, I noticed that in several applications, one actually deals with matrix equation y is equal to ax. Okay. Similarly, one deals with finding eigenvalues of the matrix. These are actually very simple problem as they appear, but it is not so practically. Again, these techniques have applications in domains like medical domain, and Google search is based on eigenvalue problem. It is all about solving matrix equation. It is all about finding the roots of some polynomial of degree n, which is basically what eigenequation, characteristic equation. So one needs essentially several fundamental techniques to be able to obtain meaningful solution. Then we started with the computerized tomography, which is CT scanning. We noticed that the problem of obtaining the underlying image can be actually posed in the form of a matrix equation. Okay, as such, this either the associated matrix runs into thousands and lakhs or millions. Okay, so no known method actually works in that such a setting. In order to, but we are interested, we need to have a solution. That solution refers to the image. Then we noticed that there is some underlying property that is naturally present. So exploiting that underlying property, one can deploy mathematical methods suitably and obtain reconstruct the image, underlying image. Then we move towards machine learning. So in machine learning, we noticed that learning is important issue. So learning is all about coming out with the decision-making rule based on the data that we have at hand. Then we noticed that there are two types of learning. One is supervised learning and unsupervised learning. So in the supervised learning, we have information about data, the property of the data. We make use of that and come out with a decision-making rule. So one such rule is what is called support vector machine, which is supervised. The other method is what is called unsupervised category. Under unsupervised category, we have a method called k-means algorithm. So while obtaining k-means algorithm, we have noticed that we normally don't make use of any information about the data points. Okay, so both supervised and unsupervised approaches have several applications in domain. There are, of course, several other ways of learning: active learning, passive learning, reinforcement learning, all this. Reinforcement learning refers to what? Suppose you start learning. Okay, in between, basically, you see the kind of learning and you can modify your learning depending on your requirements. This is, of course, very loose way of defining that. So like this, there are essentially several ways of learning, and all these ways of learning essentially lead to the deployment of mathematical technique. So to summarize, to conclude, mathematics is everywhere. In all medical domain, in all practical domains, one can see the role of mathematics. And in fact, the simple techniques like matrix equation, eigenvalue problem, so on and so forth, will play a pivotal role in many real life domain, especially in healthcare domain. So with this, I want to stop my presentation. I thank one and all for your attention. So now I invite questions. Yeah.
Sir, thank you very much, sir.
Yeah, you are welcome.
Your lesson is very much excellent. Flow is, and we cannot say how it is. With examples that you consider, everything is very fine, sir. There are a few questions.
Yeah, you are welcome. Please,
from the audience, sir. My colleague, Mr. Srinivas, will ask you those questions, sir.
Yeah, sure, sir. Sure.
Yeah. Will ask.
Yeah.
Sir, good morning. Good evening, sir.
Yeah. Please. Yeah.
I'm Srinivas Babu. There are some questions, sir, from the participants.
Yeah.
Sir, first question is, sir, can you explain how principal component analysis is applied to achieve a lower dimensional space? Shall I repeat it, sir?
Yeah, I got your question. I'll explain this.
Okay, sir.
Here, look at this matrix factorization. A is equal to U into B into V transpose. Okay, there are ways out. There are efficient ways of obtaining this matrix factorization. In fact, it is very simple. You start with the matrix A transpose. I find its eigenvalues and eigenvectors. The columns in this matrix are nothing other than the eigenvectors of the matrix A transpose corresponding to different eigenvalues. Similarly, you consider the matrix A transpose A. The columns in this matrix V are nothing other than the eigenvectors of this matrix A transpose A. The diagonal elements are essentially what? Eigenvalues of the matrix A transpose A or A transpose, both are essentially same. So one can in fact have this kind of factorization. Okay. Now for simplicity, suppose A has rank 1. When A has rank 1, it is not hard to verify that A can be written as the first column of this matrix U into the first diagonal element into first row of the matrix. The first column of this matrix is what? Of size m by 1 into first diagonal element, which is say lambda 1. So first column, which is say u1 into first diagonal element, say d11 into first column transpose, which is say v1. So u1 into this one element into this one, which is essentially what? You have how many entries here in that? This is essentially what? Outer product. First column of the matrix into one number d11 into first column transpose of this matrix V transpose. Okay, so how many elements are within here? M plus n plus 1 into R. R is equal to 1 here. So in the matrix on the right hand side, essentially you have m plus 1 number of elements, whereas in the matrix on the left hand side you have mn elements, which is very m plus n plus 1 is very small compared to mn. So this way actually one can have the information that is present in the form of mn elements in the form of m plus 1 into 1 elements. So this way one can realize projection into lower dimension space. This is simple observation, nothing big about it. So
Okay, thank you.
Did I answer your question or you want me to repeat this?
Okay, sir. One more question, sir.
To repeat, it is simple verification that when the rank of the matrix is equal to R, number of elements present in the matrix on the right hand side is m plus n plus 1 into R. Okay, so those elements actually can be arranged in the form of a vector. So to repeat, the matrix A in the vector form belongs to mn dimension space, whereas the entries in U, D, V transpose can be written in the form of a vector in m plus n plus 1 into R dimension space, which is linear mapping. Yeah, please go ahead with second question.
Okay, sir. Thank you. Sir, in slide number 29, you have defined a distance function. Can we replace that with the metric distance? It is a question.
Yeah, this is of course metric only. This is metric only. Yes. The issue is now, okay, let me answer. In fact, you can define, I did not state properties of this. I merely stated that as an example, I considered Euclidean distance. See, normally what happens, so we solve this using some simple techniques, which involve essentially derivating this cost function, all that. Those are actually quite standard. Okay, if you take arbitrary metric function, chances are that which is not differentiable. Okay, if that is not differentiable, then you have to apply actually sophisticated methods. So 2 norm or Euclidean distance is taken essentially only to have a simpler way of getting solution to this optimization problem. That is only example. One can as well take any function or any metric here. Okay, you can deploy metric provided you are able to solve this optimization problem. So, to repeat, when you take actually when I take a 2 norm distance function here, Euclidean distance function, this becomes a convex optimization problem. If I take some other distance function, maybe that this won't become convex optimization problem, right? If it is not convex optimization problem, in general, we don't know how to solve this problem. So those issues arise. But even with the general distance function, if you are able to solve this, then fine, one can deploy any distance function here. Yeah.
Oh, okay, sir.
Yeah.
I am searching for any more questions. Okay, sir.
Yeah. Okay, so if there are no questions, I would like to thank the organizers and the audiences for everything.
Sir.
I am thankful to Professor Subbara for the opportunity. I am thankful to the audiences for their patient listening. Thank you, one and all.
Sir.
Yeah.
Sir,
Sir.
thank you very much, sir.
Okay, thank you.
You are giving different examples. Very nice, sir. Thank you very much.
Okay. Okay, you are welcome. Thank you. So shall I disconnect this call now?
Yes, sir.
Yes, sir.
Okay, thank you. Yeah. Cheppandi sir, please.
Sir, one more question, sir.
Yeah.
Can we apply parabolic methods like a hidden Markov model to this image processing You
Of course,
discussed it.
yes, one can apply. Yes, of course, but I'm not very sure of application. But I came across some applications. Yes, one can apply. In fact, the Google search makes use of even hidden Markov models. There are applications in image processing, I'm sure, which actually make use of hidden Markov models. Certainly.
Okay, sir. Okay, sir.
Sir, one more
See,
question, sir.
yeah, please. Yeah.
Did there is any application of a concept of neural network in the data clustering or
Of course,
classification?
yes. It is. It has application in classification. That is supervised. See, I stated support vector machine here. One thing, a support vector machine is basically what data-driven method. You have data with the labels. This is one way of essentially grouping data. One way of actually having classification. Neural networks is another way of doing the same. Yeah, but this is my personal opinion. Compared to neural networks, I see beautiful mathematics behind the support vector machine. So it is not to say that the neural networks is not applicable. It has actually vast potential of application. The current trend of deep learning is based on convolutional neural networks. Again, behind that, actually, one can see a lot of mathematics. So one of my students is basically concentrating on that deep convolutional neural network in the framework of wavelets. So yes, neural networks actually is supervised method. Yeah.
Okay, sir. Thank you very
Yeah.
much, sir. Thank
Okay, you are welcome. Yeah, thank you. Yeah. Okay. So finally, I would like to make one conclusion. So what I personally feel is image processing, or even for that matter, medical domain, is a fertile playground for a mathematician. We can design a method, and we can see for ourselves the applicability of that method. We can see the results also. We can see the end result also. Say, for example, support vector machine, or even for that, even K-means algorithm, or even any other method, whatever I stated, even the reconstruction method in tomography. We can give mathematics. Look at, for example, this particular application. We noticed that this is, of course, our result. We noticed that the underlying matrix has very bad behavior in the sense that its condition number is very bad. Then we mathematically try to improve that condition number. Once actually we obtain the improved condition number, automatically the reconstruction quality is becoming good. Okay, so this way you can basically start with an application, then you can do some theoretical work, and again you can get back to application, and finally you can see the usefulness of your theory. So in this sense, I feel that image processing is a kind of fertile playground for us in mathematics. So this is my message. So behind all applications, there is of course beautiful mathematics. We in actually mathematics can come out with a meaningful solution, which are of course very economical. Look at, for example, tomography application. Mathematically, we are saying that a patient can be given lesser dosage. Okay, which has of course many practical implications. Okay, because scanning time actually gets reduced automatically. The harmful effect of X-rays on human bodies can be minimized. Like this, actually, one can have many advantages. Okay, by having several mathematical techniques. Okay, thank you. I stop my presentation. Thank you. Yeah.
Okay, sir. Thank you, sir.
Thank you, sir.
Thank you. Yeah. I think I did not take too much of time.
No, sir. No, sir.
No.
Sufficient time. Sufficient.
Okay. Thank you. Yeah.
Thank you, sir.